Greetings, everybody. Thanks for joining us today for the ANSYS Twin Builder webinar. I will begin in just a moment. Okay, here I go. Thanks for joining today. We'll be talking about ANSYS Twin Builder. We're going to talk about how to build, validate, and deploy complete system simulations and digital twins. Our presenter will be Stephen Anchong Liu from Ozen Engineering, and this is Chris Cowan here to introduce my company for a moment. What does Ozen Engineering do? We're focused on simulation. We use finite element analysis tools, computational fluid dynamics, and high frequency and low frequency electromagnetics to solve multidisciplinary engineering problems. And I'm proud to tell you that we are an ANSYS Elite channel partner, and for the current year, we have been selected as the channel partner of the year. As a channel partner, we sell ANSYS software tools. We provide training, technical support to our customers, and we provide consulting services worldwide. You can see here the full suite of ANSYS simulation tools that we work with. Every week or every second week, we present a webinar on a simulation topic. You can see that today's topic, Twin Builder, is actually our last topic of 2019, and we'll come up with a new schedule for 2020. You can see here a list of the various topics that we have presented on for the last half year or so. And if you want to access those, you can on our website. On our website, ozeninc.com. Under resources, you can go to the webinar library, or you can type in directly webinar library. That will bring up our list of webinars sorted by physics. And at the same time, if you're interested, you can subscribe to our newsletter, which we send out maximum once a month usually, to notify customers and interested parties of upcoming relevant events. Relatively new introduction from ANSYS is the ANSYS Cloud. What this does is provides native support to cloud solve resources for users of ANSYS Mechanical, Fluent, and Electronics. If you have rather large problems to solve and you want to solve them quickly without purchasing the software to enable you to solve those quickly, that's the perfect application for ANSYS Cloud because it gives you one-click burst to the cloud, and it's built natively into the tools. One other thing I'll tell you is that Ozen Engineering is putting on a technical conference related to ANSYS simulation in February 2020. This is going to be in Mountain View in the Silicon Valley, and we'll be talking about topics with a focus on digital twin, additive manufacturing, 5G, and Internet of Things. If you're interested, you can join from our website. So, information on how to contact Ozen Engineering: you can email us info@ozeninc.com. You can call us directly to speak with an engineer or an account manager. And for if you're aware of anybody, an electrical engineer or mechanical engineer who is interested in joining our team, we're looking for someone with specialization in digital twin and embedded systems. So I'd like to introduce to you Anchong Stephen Liu. He works as an electrical engineer supporting the electronics products with Ozen Engineering, and he received his bachelor's degree in electrical engineering from University of California at Santa Barbara. So the GoTo webinar user interface allows you to submit questions via chat or the questions panel. Feel free to do that. And meanwhile, I'll turn it over to Stephen.
Okay, great. Thanks, Chris, for the introduction. Just give me one moment. I'll quickly share my screen. Okay, so today's topic is about digital twin. So just briefly goes through our agenda today. I will go through this presentation of the overview of uh, Twin Builder. The software is called Twin Builder. And after the presentation, I will show you guys a simple demo we put it together here at Ozen Engineering. So first of all, what is a simulation-based digital twin? So essentially, it is a connected virtual replica of an in-service physical asset in the form of an integrated multi-domain system simulation that mirrors the life and experience of the asset. It enables system design optimization, predictive maintenance, and optimized industrial asset management. ANSYS Twin Builder for digital twins and the predictive maintenance. Uh, uh, Twin Builder is a new product for predictive maintenance. It so what the benefits of of using Twin Builder in your system is one thing is that you can save on warranty and insurance costs, uh, optimize your product operations, and implement predictive maintenance. And how do we achieve that? Uh, so first, you want to build a twin that reuse the engineering know-how to build accurate virtual product replicas. We can. You want to also validate the twin, validate and optimize the twin model. And lastly, you want to deploy the twin and connect and deploy this twin, uh, connect and deploy to supported industrial IoT platforms to connect with your physical device. A quick overview of the Twin Builder technical capabilities. So here we basically divide the capabilities into three phases. So that's build, deploy, and validate. So we'll go through each of these separately. So first we have the build phase. The benefits and the capabilities are here. So one is it's easily assemble virtual replica from a variety of sources. It is multi-domain, multi-fidelity, and a multi-language. Uh, the capabilities uh, are as follows. So one is that it's supported for multiple modeling domains and languages. It has extensive zero-D application-specific libraries, and it has a third-party tool integration capability. It also allows the 3D reduced order model creation and integration. And lastly, is embedded software integration. So speaking of multi-domains, one of the capability is multi-domain systems modeler. Uh, as you can see on this slide, there is a lot of there's a lot of different languages and domains. From the top, we have multi-domain systems. That's a sophisticated system that has circuits and components. We have a simplified block diagrams. We also have C code and FMUs. FMU stands for functional mockup units. Um, we also have code simulation. We can also import test data as your input data. So you can specify your X and Y based on your test data and excite your system with the test data. Which it's Twin Builder also supports Modelica language. Also, you can build up your circuits. This one, it's like it's like a switching circuit. Down at the bottom, we also have reduced order models. You can and lastly is digital mixed signal. So you use block diagrams with logic gates uh, to do a digital mixed signal analysis. Um, Within these different system modelers, we mentioned something about the ROM, uh, about we mentioned something about ROM and co-simulation. So those are achieved based on the comprehensive platform ANSYS provides. So at the top, we're looking at the system, which represents what the twin builder is trying to achieve. And downstream of this tree, we look at a platform with multi-physics. So uh, this multi-physics supported platform, it includes all the physics that ANSYS provide, from fluids to structures, electronics, semiconductors, and embedded software. So all these different physics flagship products of ANSYS can be integrated or co-simulated with Twin Builder. They also Twin Builder also includes extensive 0D application specific libraries. So as you can see, we have ready-to-go libraries for uh, for components of different industry. We have control systems, hydraulics, mechanics, digital, electrical, and power systems. We also we also have the libraries for manufacturers, automotive, aerospace, heating and cooling. So essentially, this is a multi-domain model libraries and tools available for you to use in Twin Builder. So you don't have to, and of course, upon so how to use these models are really simple. You basically just open the library and drag and drop it on your diagram, and upon that you can also change the attributes and the specifications of different components. Um, we also mentioned something about ROM, which is stands for reduced order modeling. Um, it is one of the important approaches for connecting 3D physics simulation to the system level. A ROM, what a ROM is, that it is a simplification of a high fidelity dynamical model that preserves essential behavior and dominant effects. For the purpose of reducing simulation time or storage capacity required for the more complex model. So in terms of creating a ROM, there is not a single ROM technique. Rather, there are many approaches that apply to the different engineering disciplines and applications. So it could be static, dynamic, linear, or non-linear. Um, so as you can see, all the physics within ANSYS, mechanical, electrical, electromagnetic, thermal, and fluid, they can all be created into a ROM model uh, in many different ways. So I guess the key point, the keynote taken out from this slide is that this by doing this ROM, it preserves essential accuracy and simulates in a fraction of the time required by 3D. And it is a technique that's available for all the ANSYS physics. Uh, so 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 in the normal simulation, a FLUENT CFD simulation, for example, this is a pipe fluid simulation. It took about 3 hours on 12 cores, and after the ROM simulation real time, it solves in seconds. So implementation of the ROM. It is independent of the solvers. The solver solves the problem and then use the ROM builder, and um, it is it is not impacted. The solver is not impacted by the ROM method's development, and the ROM for nonlinear steady and transient 2D 3D simulations. ROM is can also, uh, as we said, are all capable. Our ROMs are all available for all the solvers. Physics of ANSYS, mechanical implicit, explicit, CFD, Maxwell, thermal, acoustics, or even coupled physics. For example, fluid structure interaction. Uh, a The workflow of a ROM creation would be, on the left side we have the 3D simulation tool, and you can do that's the ANSYS source 3D tool, or you call it, and then using the tool you get a 3D simulation data. That's the normal, that's the traditional simulation uh, idea we're talking about. We're just doing a regular 3D simulation, and then we can using you can also do a parameter sweep on the simulation, and you specify different parameters on the input and output. Then you can train the data from ANSYS to TwinBuilder, do the ROM extraction. This extraction takes, rather than hours or days, it will take only minutes. So once the software is trained by the data, you can extract this ROM. Then you will end up with a ANSYS ROM model. That will be just a like a .fmu or just a Maxwell project. Then you can just import that into your TwinBuilder. That comes to the ROM consumption. In TwinBuilder, you have the system simulation using either FMU or the digital twin. And at that time, the ROM consumption will only take seconds to complete the task. How do we import a reduced order model into TwinBuilder? Relatively easy. You just go to the top menu bar and click on TwinBuilder, and there's sub-circuit. You have all these options to import your ROM. So for different physics, it's a different name or it's different file type, but essentially the idea is the same, that we are using a reduced order model to depict or to model the actual 3D simulation. As you can see, it includes Simulink component, MathCAD, and Maxwell, all the way to SCADE, FLUENT. We also have FMU component. Usually this will be used for fluid. Data connector component, that would be the data connection component in order for digital twin to talk with outside world, uh, like the physical, to get, for example, acquisition of data from the physical device or from a Python script or from a online web page. You basically just name it, the data connector connects it. So that's the basic idea, and then but on the naming side, there might be a different name. So on the for these for these tools, we call it a co-simulation link. On these solvers, we call it a reduced order model. So how to couple a ROM with a system model? As you can see, this is a mechanical system that has supports loads and thermostatic and a heat source. And then right here in the middle, the mixing T is the ROM model that we imported. And as you can see, you can hook it up with different components. And by just looking through this, I think most of the components we see here on this slide are from the TwinBuilder library. So yeah, it is if you're familiar with the tool, creating a schematic probably just takes a couple minutes to an hour. Relatively simple. Coupling a model around with a system model. So you ha- we have the as on the previous slides we have this mechanical system. Then we turn this entire mechanical system into a two-way in, two-way out Modelica model, and then we connect it with a response surface in the twin builder. So as we can see here, there's T in from the system. That would be a temperature from the system that would bring the data into the ROM and in this port, and the ROM would output the temperature out from the ROM. And we also have the DP out, DP from the ROM, and we have, and then on the outer side of the input, we have M dot from system. I don't have, I'm not sure what these two stand for, but those, just consider that as another input and output. So uh, the simple idea is here. Then we go to the second phase, which is the validate phase. The benefits and the capabilities are listed. So the benefits is that one, we can, on an industrial level, the benefits would be you can ensure product reliability and robustness and optimize your product design. Capabilities includes multi-domain simulation with integrated post-processing, rapid HMI prototyping, system validation and optimization, and XIL integration. Rapid HMI prototyping. This is a capability from ANSYS Skate. So and then the product is called a rapid prototyper that can enhances the simulation experience with powerful, easy to design, and interactive graphical panels. So in a system modeling simulation on the right, we see there's a system. You can ignore the plots surround it. So these are just the plots of different ports or on different components or different variables. Um, this whole system, once you have it built and start to analyze it, there's, as you can see, there's also a panel. This panel will pop up, and you will be able to, oh, there you go. You'll be able to play with the slide bars or enter value, or so this is a relatively sophisticated panel that ANSYS created. So a lot of the parameters and you can play with, so that you can control the entire system in this panel instead of uh, change the values uh, by double clicking on the components or change the value internally. Everything can be summarized into this panel. System validation and optimization. You can easily integrate and validate with test data. So this is a battery simulation. So you can see there's a lot of the cells are formed into a group, and then or cells formed into a pack, and then the pack forms into a entire battery. And you can have you can compare your simulation and the test data and put them on the same plot. You can also optimize your system performance with built-in optimizers. Either use ANSYS Design Explorer or ANSYS OptiSlang. So you can plot your you can have your results plotted with different parameters. Lastly, we have the third phase. That's deploy phase. The value of the capabilities are, the value. You can optimize your operations. You can also deploy for predictive maintenance. The capabilities includes quickly connect to supported IoT platforms and export and deploy generated models. So at this phase, Twin Builder um, can really has performed to its peak value, which is making them a digital replica of a physical model. Uh, and it can also predict your maintenance time. For example, one project insisted with GE. They have a couple motors uh, in on a on, they have a winged generator in the middle of the ocean, and there's various motors on it. And then what ANSYS provided was a solution that to create digital replicas of those motors and connect them with the so-called IoT platforms. And without sending people without actually sending people to onto the site, we can predict whether the motor is functioning well, is functioning the right way, or if there's any maintenance needed on the motor. So this is at the point where we talk about the data connector. So uh, relatively simple. Uh, you you same as the other ROM subcircuits. You just use the data connector subcircuits, and you will be able to drop a box, and then you can define how many number of outputs from the Simplorer and number of inputs into the Simplorer, and then you basically just specify the port number, connection timeout, and the sample time, and then there you go. You will have a connection point in Twin Builder with outside source or outside data. So for these data connectors, Twin Builder has their built-in data connector. You can also, if it's a sophisticated project, you can use ThingWorx, Predix, or SAP, because these are the IoT platforms that partner with ANSYS. And then for a example like this, we can export from Twin Builder to generate a portable and a cloud deployable twin. Okay, so let me demonstrate a simple example that we created. So here we have a Golden Gate Bridge analysis using raw model in Twin Builder. So what we did is since Ozen Engineering is located in Sunnyvale, we are a Bay Area based consulting company. So we are interested in the culture here in the Bay. We took this Golden Gate Bridge model and tried to do a CFD simulation. First we start off with a simplified CAD model, as you can see on the left. So the ropes and then the cables are being neglected for the computational purposes. The main goal of this work is to create a model that captures the pressure on the bridge under the wind effect. So there will be wind at the bay, and those wind creates pressure on the bridge, and we want to use Twin Builder to model that. For the bridge, we have different names on the models. So the actual bridge where the cars are running on, we call it the bridge. And then two These two are called interior tower, and then these outsider ones are called exterior tower. Then we'll skip this about why using Fluent. So just a little bit about the model info. So basically what we did is that we started with the solid model that depicts uh, the ocean and the land at the Golden Gate Bridge, and we put the Golden Gate Bridge model on top of the solid model. Then we created a fluid domain on top of the solid model. So the wind will so there will be wind propagating through x and y direction, but not the z direction. Uh, the mesh, close look on the mesh. Nothing much to emphasize. But you can see on the bridge boundaries, the mesh are getting denser at the cross sections. And the full model would look like this. As I said, the wind the wind will propagate in this fluid domain, and what we take as input is the velocity and the direction of the wind. This is the CFD. This is a results visualization in the CFD tool. So in CFD we're able to visualize air velocity streamlines and as well as the pressure on the bridge. Once the simulation is done, we can, as we said, we can export a ROM in Workbench. So what we do is, okay, first in order to create the ROM in the simulation inside the Fluent, the user need to activate the Fluent ROM feature. Then you hit the simulation, and when the simulation is done, inside ANSYS Workbench, simply drag and drop the 3D ROM block and underneath the Fluent block, and then a diagram will pop up look like this. And you basically just prop it and then make sure all the green checks are checked. Then you can then in order to make sure the green checks are all checked, you want to do a design of experiments. So here, the inputs are defined in Fluent. And we need to define a range of each input and the total number of design points. So basically, it's just telling the software it's teaching the software what the input ranges are. So for this example, we are setting the velocity to be plus minus 40 miles per hour, 40 meters per hour. Sorry, 40 meters per second. That will be the range. So that we call that design points based on DOE. Essentially, this ROM becomes a matrix with a linear matrix. After the design of experiment is done, we can simply export the ROM. This will become a .fmu functional markup unit, and you basically just add this functional markup units in the twin builder. And there you go, you come up with a schematic like this. So the ROM, the FMU is essentially this block. Here I have defined a lot of outputs and just two inputs. The input, as you can see, is called velocity x and the velocity y. It is so on the okay, excuse me, the order is wrong. So I will go with the data connector first. So on the left we have a data connector. This data connector reads the weather data from near Golden Gate Bridge, and what it reads is essentially the wind speed and the wind direction, and these will be the inputs to this twin builder. And then I use two functional blocks to manipulate these two data, uh, so that the input into the actual ROM would be velocity component X and the velocity component Y. And then on the output of the ROM, the bridge ROM, we can specify you however you want to specify it. But at the beginning, we're saying we're just interested in the pressure on the bridge and interior tower and exterior tower. But of course, you can also take a look. You can also take a look at the velocity of the domain air, or the pressure of the domain air, or the shear stress on the tower as well. Where I was talking about the data connector, where we get this, where we get the uh, the online weather data. This is the online weather data we're talking about. So this website updates the weather data every 5 minutes, and we have so in this so in one of the so we have a lot of setups. So one of the setup is that we ask the twin builder to read the history data on the online website for the past 2 hours, and we ask the twin builder to acquire additional data as the website is updating. Um, the live data is sent in every 15 seconds, and as you can see, this is all the inputs into the twin builder. So on the top two is the wind speed and the wind direction. That is from strictly from the website. Um, then these two are the data manipulated based on these two and sent into the ROM. So this will be the velocity x component and the velocity y component. And then we can take a look at the pressure on the tower and the bridge, and the shear stress on the tower. We can either plot them in a stack up way or all in one plot. So that was it. And then if we go to the twin builder, this is the demo. This is the case I was talking about. So if I were, so how do we analyze? So how do we analyze this? Um, so everything is ready to go at this moment. Uh, for example, this is the input as we saw. We have so um, okay, everything is ready to go. So what we do is we hit analyze, and then the simulation will start prompting. Meantime, we want to open a command prompt to feed in the data. So right now, what I'm demoing is not okay. At this, so as you saw, I hit the analyze button, so the simulation has already started. At the bottom and in the progress window, we can see it says the project is initialized, and what it's doing is that it's waiting for my data to feed in. So this climb3a.python is the Python script that I wrote to acquire data from that online source. So what I do is just hit enter, and then my Python script will start. And as you can see, we have data sent to Simplorer at the speed of 50. The speed is 15, and the direction is 130 degree. And we also have this message says received from Twin Builder. Uh, this is this is a function that we're not using in this case, but what it is it's really just this lag. So if you want to have an interaction with your physical device or outside source or whatever whatsoever, you can make a loop out of it, feed your simulation or ROM data results back to your data connection, and you can kind of having a feedback uh, feedback mechanism. But right here, I'm not using this capability. So as you can see, the data are being feed in. So as you can also see, the input is changing every 15 seconds. And as you can see in the stack up plot, uh, this is change the pressure results on the bridge and exterior towers and the shear stress are changing as well. So a general takeaway from this case study is that we are essentially showing the capability of a data acquisition in TwinBuilder. This is although this is pretty primitive because it's only just a online data source, but the idea is that we want to show TwinBuilder is able to acquire all sorts of data to make the connection. As Chris mentioned earlier in the introduction, we are having a conference in the upcoming February, and we are trying to build our center of excellence for digital twin. And with that being said, all our engineers are working on one or some of projects to make a physical digital twin demo. So if you are interested, well, you are always welcome to our conference. It's on February 19th. Um, something I some something else I can share with is that other than reading data from online source, we is we also tested. We're also confidently telling you that we can read source from outside device such as a Raspberry Pi or power supply or a thermocoupling thermometer. All sorts of sources can be manipulated and transferred into TwinBuilder. So the next thing would be make a good model for your simulation and basically just follow the steps and follow the three phases that I presented earlier. And we are sure and we and ANSYS are sure that um, at some point this will help you to enhance your product development or optimization or operations at some point. Um, that is all I have for you guys today. Is there any questions or comments? Feel free to uh, raise your hand or leave it at the question sections. Okay. Hands raised. Is there any questions? Excuse me, I saw a hand raised, but I don't know if you have any question. Is that Sing? Okay, seems we are. Oh, here we go. There's one question. Questions from Niar. Yes, can we speed up the solve by using HPC? Of course. So Well, actually, oh, sorry, you're talking about the solving twin builder. Then that's a no. Um, because I believe if we look at this, there's no option for HPC. So no, in twin builder, no, it is not utilized in HPC, but in the simulation, yes. Can we use the HPC for simulation? Uh, I'm not sure which part of simulation you're talking about. Are you talking about the simulation in Twin Builder or simulation generally in the physics? Because in different physics, either mechanical fluids or electromagnetics, you're always able to use HPC as long as you have the license. But for the Twin Builder, no, it does not use HPC. Okay, guess. Is there any more questions? Okay, if uh, okay, that is all I have for today. Thanks for your attention. Thanks for joining Ozen's webinar sessions. Oh, seems there's one more question. We would like to know if the Twin Builder can provide results fast, fast enough so we can predict 4 hours in future. Uh, I'm not sure this fast. How do you define this fast enough? But in terms of predict 4 hours in future, I believe so. I think what you will. So that's so that so okay. So that I think you don't have. That will not be a real time simulation. So I think what you define will be you can define the end time, which is the duration of your simulation in Twin Builder, and then you define your minimum time step. So I guess that depends on how accurate you want the time step to be, or other words, how fast, what's the rate of like how fast your input data will change. Like, is your system sensitive enough that your data changes at a rate every seconds or every 5 minutes, or your data is constant? You're just trying to see the cumulative effects on your system. So that really depends. But what I can say right now is that you can define your simulation time. So you're talking about 4 hours in the future. So what I would do is just specify the simulation time as 4 hours, and you specify your minimum and maximum time step. And this won't take you up to 4 hours. This will probably, well, it depends on, or also depends on how complicated your ROM, your systems are. But it shouldn't take up to 4 hours. And also another thing is that if you want to predict your predict things in the future, you are expecting to read real life data, then the minimum time step. So the minimum time step for data acquisition. So if you're just feeding data through your, say, test data, or a so if you're anything but your real life data, then I think that's probably fine to speed it up. But if you are trying to feed in real life data, the minimum time step data connector can recognize is 1 second. That is That is what I can say now. In other words, the simulation has to run faster than the real life events. Understood. Uh, yeah, the simulation is should be fast enough. It's really about the uh, it's really the data connection, like how fast the rate is for the data transmission. But yeah, as you can see, like as soon as I try to, as soon as the data is being fed into my ROM, the data pops out pretty much like instantly. So as you can see, if this is about what 5 minutes. So yeah, I would say yeah, it is possible. Yeah, if you have uh if near or any of other of you guys have any questions, feel free to email us or call us in. Our email is, I believe it says right here. Our email is ozeninc or info@ozeninc.com. That's also fine. And you can call us or feel free to visit our website. Okay, I think that would be all. Yeah, thanks again for your attention. Have a wonderful rest of your day.